Hello everyone, thank you for attending Oracle's Developer Live. Today, I'll be talking about an exciting new service that we are launching in Oracle called the AI services. You'll be using this service to detect anomalies in enterprise data. My name is Ranjit Narayanan. I'm a director of software development for Oracle Cloud. Let me remind that this session and the material used today is going to be about a product that's not yet released. The timeframes, the development cycle, the features are all subject to change during the course of the year. I'll be taking a few questions at the end of the session. With that, let's start the session. First, let's take a look into OCI AI services. A quick reminder of what AI services bring to OCI customers. OCI AI services make it easy for developers to apply AI to their applications without learning data science fundamentals. Typical data science teams have to work across boundaries. These boundaries include developers, these data engineers, operators, and data scientists. OCI AI services enables collaboration between these parties. With OCI AI services, you can start with great models and then customize it with both domain knowledge and customer data. OCI AI services enable us to create machine learning models that span both application and services. What this means is that you don't have to be a machine learning expert to build models using OCI. Great models can be created and trained by any developer. Now let's go into OCI decision service. OCI decision services involves use of machine learning fundamentals, statistics, and analytical techniques to help the customers build and make decisions out of data, judgments, and decide on the future course of action. OCI offers a suite of services under decision support that will help enable customers integrate this data. And just like the other AI services, the goal of the service is to be able to create models and set them up without an in-house team of AI and machine learning experts. Now, let's deep dive into some of the features of OCI decision service. The first service, and what we'll be talking about during the rest of this presentation, is anomaly detection. Anomaly detection is identification of rare items, events, or observations that raise suspicion that differ significantly from the majority of data. There are three different types of anomaly detection that we are targeting in OCI. The first part is about multivariate anomaly detection, where data comes in time series across multiple variables. The second part is making sense of anomalies in data which have only single variable called univariate anomaly detection. And finally, we will be building anomaly detection for non-time series data. We will also be building services in the future deal with forecasting analytics, fraud detection and prevention, recommendation systems, and content moderation. Today, we will be deep diving into anomaly detection. Anomaly detection is a new OCI service feature that's currently in development, and it's targeted to be available across all Oracle Cloud regions in calendar year 2021. First thing to know about anomaly detection service is that we don't store any customer data. The service is written to provide built-in data isolation. It's based on Oracle's patented innovations for various pre-processing, post-processing, model training, model tuning, and anomaly detection algorithms that make up what is called the MSET2 portfolio. MSET2 helps in proactive detection of anomalies with ultra-low false alarm and very small missed alarm probabilities. We will go deeper into MSET2 during the rest of this presentation. Anomaly detection service also helps perform intelligent data pre-processing on low quality and low resolution data. This enables us to improve the quality of the trained models, even though the data sets that we are training on does not have the high quality. Now it's time to go and take a look at how you can train anomaly detection models using OCI. The first use case we'll be looking at is a customer with a low volume of data. A rule of the thumb here is that if the data rate is under 100 transactions a second, you can use this use case. There are three major steps involved in training an anomaly detection model with OCI for this use case. The first step is to upload the raw data into object storage. We also support other cloud storage solutions like Oracle ETP and various third-party sources like time series databases such as Influx. The next step is to use the data that's been uploaded to train a model. Training starts an asynchronous process in the Oracle Cloud, which involves multiple steps, including pre-processing, the actual model training, and the storage of the model. The stored model is stored inside Oracle's cloud and is used whenever there is a request for detecting anomalies. The third and final step is the detect part, wherein a pre-provisioned compute cluster is created based on the trained data that has been stored. The model is dynamically pulled into this pre-provisioned compute cluster. This enables the customer to scale and the developer to not worry about the number of instances or resources used to create and serve this model. This pretty much works like a serverless system. Cached instances of the model help in decreasing the latency of further calls. A note here, all these calls are based on HTTP, but we will talk about more scenarios other than HTTP in the further session. Now let's talk about the next use case of a customer with a high volume of data. The basic steps for a customer for high volume remain the same, except there's an additional step to deploy the anomaly detection model into a dedicated compute cluster. By calling the deploy API, a customer or a developer can deploy the model into a cluster which is only served for this particular model. This enables high-scale scenarios, which follows the rule of the thumb, and be able to train customers' model across multiple instances which is dedicated to this particular model. Last but not the least, we talk about customer with a streaming data requirement. Anomaly detection service also supports end-to-end streaming, and we use the OCI streaming services to support for streaming use cases. This enables high volume of data to be processed without the developer worrying about windowing or streaming functionalities. Customer data from different sources, including IoT, media, healthcare, or finance, can be pushed to an OCI stream. And these streams, while they're configured into the OCI AI services, are automatically pulled by the anomaly detection components. And the anomalies detected, therefore, can be consumed by sync component. The sinks, or the output sinks, include dashboards, notification systems, and alerts. Therefore, you can provide an end-to-end experience of the anomaly detection using streaming service. Now let's go into a demo of how the anomaly detection service works. Let's take a look at the sensor data in the training information. Here are 10 sensors, and within the input data, you have timestamps, which include at what point the sensors have emitted the data. For example, the first sensor has emitted a particular value at this time, and so on for the 10 sensors. Now, in real life, sensors always have inconsistencies in their output. For example, sensor 10 here has missed an output here where you see a NaN value, and a NaN value here as well. Sensor 10 has got some missing values. This is actually better if we can visualize the sensor in a graph. Here is an output visualization of the sensor values across all the timestamps that we have. As you can see, there are about 400 timestamps, and there are some inconsistencies in the data. Two things I want to point out are here are missing values in sensor 1, gaps in the value here. Similarly, sensor 3 and sensor 10 also have few missing values. Sensor 7 and sensor 4, on the other hand, are at a very low resolution. As you can see, the data floats between 2 or 3 different points. Now, in real life, we always expect data like this to be a part of our regular historical collection. However, the OCI anomaly detection service is able to work across these sensor value inconsistencies and still able to train the model. The first step, as I discussed earlier, is to upload the data into object storage. Here, I've already uploaded the data into object storage. And as you can see, the training data file is uploaded. It is under a particular bucket and namespace. Now I'm going to use Swagger to actually call the anomaly detection service. We will use 3 of the HTTP APIs today. First is to post on anomaly detection to train a model. Second is a get on the anomaly detection call to return the status of the asynchronous training job. And finally, we will be using the detect API to actually detect anomalies in the model that was just trained. Take a look at the post request. The post request contains JSON payload that points you to the location of the training information. In this case, I've already pre-populated the information for the particular bucket and the object used for training. Here is a description and name of the model for reference purposes. Now let's go ahead and execute this call. As you can see here, the model has started training, and you'll get some output about the details of the model. The most important piece of information that you get out of this is the OSIT, or the ID of the model. I'm going to copy this out to check the status of the model in the next call. Now let's check the status of the model that we just created. I'm going to overwrite the given model with the status with the model ID from the previous step. The moment I execute this call, I can see that the model is running in the background and it is still training. This model, based on the amount of data, is going to take a few minutes to train. So what I'm going to do is I'm going to use a model that I trained earlier today and continue this process. Going back to the model ID parameter and using something that I'd already trained. Executing this call again, you can see that the model training has already been successful and the lifecycle state of this model is trained. You can also see that it's also based on the same set of sensors, and you also have some additional information which talks about what sensors are used and what sensors are dropped. You also have a limited knowledge of model metrics, model training metrics, FAP score. We'll come to the details of the FAP score later. But please note that the current FAP score for this model is 0. Now let's try to use this model to actually detect anomalies in data. For that, let's go back and let's see if we can find some data for detection. Here is output of the same set of sensors in real time that we'll use for detection. And as you can see, it follows the same schema as the train request. We still have the 10 sensors and they're emitting values at a particular interval. You can see here, it's pretty much emitting values every minute or so. And I believe this has got around 500 timestamps, about a few hours of data in this detect. In detection also, as you can, similar to the train phase, you can see that there are some missing values possible because in real life, you always have inconsistencies in your data set, even whether it is recorded or in real time. So what I will do is copy this data and use it for training the model. For this, I use the detect call, and I'm going to paste the model, the training data the detection data that I use, and I'm going to go back to the step and copy the model ID. And execute this request. Here you can see that in the output data, in the detection data, we have the service has identified anomalies. Anomalies is identified in sensor number 5. And here is a timestamp of the anomalies where the actual values are, what the actual value was, and what the estimated values are. I can also download this response and try to show it with some details. Now let me try to visualize these anomalies. We use a custom tool to visualize anomalies, wherein we first paste the result of anomaly detection. And then I go back to the original data, and I'm going to paste the input to anomaly detection. And once I plot the graph here, you can see that there are 246 anomalies detected in sensor number 5, and that's the only sensor that has outputted anomalies. You can also plot all of these sensors and the current sensor to actually see a visual representation of how the anomalies look like. In fact, even visually, we can figure this out, that among all the sensors, only sensor number 5 is not working properly. And at some point of time around 11:15 or so, the sensor started misbehaving, and what the estimated values are shown in green, and the actual values are shown in black. Also zoom in and analyze some of the details of the anomalies that we just saw. That brings us back to the end of the demo, and let's continue into the deep dive of the anomaly detection service. Now let's talk about what is running behind the scenes. As we discussed earlier, the anomaly detection service is powered by the MSET suite of algorithms. Oracle has made extensive use of MSET algorithms for data centers and a bunch of customers across multiple sectors. Oracle's prognostic solutions are robust to low-resolution sensors, data acquisition limitations, missing values, spurious anomalies, signal asynchronous issues, etc. We are able to figure out that MSET attains higher sensitivity and better false alarm avoidance than any machine learning approach that we have tried before, including neural networks, support vector machines, kernel regression, and even LSTM. Therefore, we believe that MSET suite of algorithms are able to provide some value add for prognostic applications. Examples are higher plant availability, higher yield, shorter life cycle, and lower early life failures. Let's go into what is MSET. Multivariate anomaly detection that we demoed and discussed today is comprised of the MSET suite, which contains 3 different parts. First is MSET, which itself stands for Multivariate State Estimation Technique. MSET uses estimation based on statistical pattern recognition to figure out what is the normal operating state of a system and establish a relationship between different parameters or sensors in this case. The estimations from MSET are used to drive anomaly detection in the rest of the MSET 2 suite. The second part of MSET 2 is IDP, which stands for Intelligent Data Preprocessing. IDP is a set of data preprocessing techniques that increase the quality of input data. As you saw during the demonstration, both the input data and the training data contained quality issues, and we are able to automatically fix those issues and be able to train and detect anomalies in the data. That's powered by IDP. The third, and but least last but not the least, SPRT is the third method used for statistical hypothesis, and that determines sequentially which observation is an anomaly and which is not. Some use cases that MSET has already or already worked before are smart meters, energy efficiency, a lot of utility scenarios like underground and overground cables, wind turbines, batteries, load forecasting, circuit breakers, transformers, substation monitoring, cybersecurity, and solar panels. Now let's look into how exactly MSET works with early detection of anomalies. In any prognostic manufacturing solution, the number one value add is the ability to detect anomalies early. More than the loss of the equipment or the cost of the equipment, the most important value add is the operational continuity and service availability. MSET 2, when working against such real-time data, it helps detect anomalies very early. How it does that is by creating a dynamic band around sensors in real time and correlating sensors between different values. As you can see in the picture, traditional monitoring, which is either statistics or rule-based, use threshold or different kinds of monitoring techniques to find out where anomalies are. In traditional monitoring, you'd only realize that there is a failure all the way up here. Whereas with MSET 2, you're able to detect anomalies very early, and you're able to tell the customer that there is a potential failure for the system that's protecting or that's underneath the sensors, and you can give an early warning to your customer. Next, let's talk about the second technique, IDP. IDP, or Intelligent Data Preprocessing, is used because in real life, we have a number of inconsistencies in the data. You have, like you see on the picture on the right, different types of sensors. They all work in different ways. And when you collect and collate all of this information, there's always errors that happen in the sensor signal. For example, you may get false signals or low correlated signals. You may have signals that emit data at a different rate. You might have some sensors malfunctioning for a short time or for a long time. And finally, you may also have low resolution sensors, as we had seen in the demonstration. IDP methods enable automatic fix-up of such inconsistencies. Therefore, the goal is that the customer does not have to worry about fixing the data before they bring it to the anomaly detection service. Here we go deeper into one of the techniques for IDP called Analytical Resampling process. ARP or Analytical Resampling process helps dealing with different signal rates. For example, you see two signals here, one in blue and one in red, which are out of sync. And passing through ARP, we provide uniform sampling across the time series data. The next technique we'll go into is missing value imputation. MVI is used to fill in missing values in any time series data whenever there are gaps in data. As I showed you in the demo, there were some gaps in sensor 10. And here's a deep zoom in on sensor 10 values. And as you can see, MVI uses a combination of interpolation and MSET estimates to figure out what the missing values are so that their automatic fix-up of data happens. Last but not the least, Un-Quantization is the final technique of IDP that we'll talk about today. And here is an input and output sample, how the IDP sensors look like, how the sensors look like before and after un-quantization is applied to IDP. As you can see, the sensors are sensor 4 and sensor 6. They oscillate between few discrete states, but un-quantization figures out the inherent values for these sensors that is used for model training and for anomaly detection. And therefore, you get a continuous signal that looks like the picture on the right. Now let's talk about the third algorithm, SPRT. SPRT is a traditional statistical method used for anomaly detection that has been around for decades. A pattern recognition technique with high sensitivity, high reliability, and very good surveillance success rate. Developers have proved that SPRT has worked across mathematically for a number of decades, and even with noisy input variables. The way SPRT works is that its input to SPRT is the output of MSET combined with the differential operator. Therefore, the residual is passed into SPRT, and SPRT triggers the alarms created by the MSET2 suite of algorithms. Now let's look into some model input and evaluation metrics for the MSET2 model. The key input factors for training an MSET model are number 1, the number of sensors, and number 2, the number of timestamps used to train the model. The output metrics are the major of them we talked about are false alarm probability, or FAP. I showed you that the FAP value for the model trained for the demonstration was 0. FAP stands for false alarm probability, and these are signals that are detected as anomalies, but in reality, it's not an anomaly. When you have an FAP of 0, that means you got a near perfect model. Missed alarm probabilities are alarms which are missed by the system or the service, but it's actually an anomaly. This is another metric to figure out how the MSET2 model works in real time. Now let's go into some code samples and deep dive into how you can use the anomaly detection service against OCI using your code. For this sample, I'm going to use OK-HTTP library and use Java to call all the anomaly detection models. Here is a call to the train model endpoint, and what you need is input as a base URL of the anomaly detection service. I'm using first the OK-HTTP client, setting it up, and creating a media type of JSON. As I showed you during the demonstration, the request body is JSON, and it contains the most important parameter in the request is the pointer to the actual training data. The training data, in this case, I'm uploading to object storage. The request is made to the combination of base URL and a suffix, and you call a post API on the request. The output of the HTTP request gives you the anomalies, the anomaly model that's obtained. The most important part of the output is the ID parameter, which, as you have seen during the demonstration, is used in the next steps. And we'll also use it in the further code samples. Next, let's look at how the status of a trained model can be examined using code. You need the ID parameter from the training step, and you also need the base URL of the anomaly detection service. This time, you create a request URL by combining the base URL suffix and the ID parameter. And all you have to do is call get HTTP call on this particular URL generated and check out the status of the request. Next, we'll talk about how to detect anomalies in the data that you have you're trying to test. Here again, we need the ID parameter as an input, and I can use the data that is being where I need to test out anomalies in as a parameter for this function. You pass this time text plain media type, and we can pull in the detect data in line. It could be in UTF-8 is a format that we use, based on whatever format you want. You should be changing the encoding of your HTTP request. Now you consider the URL, which is a combination of the base URL, the path, and the ID that you just got from the training the model. You make a post request with a body that contains the payload, which is the detect data. And the output of the response output will contain the anomalies within the JSON object. Anomalies is the object that you should be looking for within the response, which contains both anomalies, the name of the sensors, and the timestamps for the anomalies are detected. Next, let's look at how do you deploy the anomaly detection model into a particular dedicated set of services. The deploy call here takes the same parameters as before, the base URL and the ID. And this time you are going to use JSON media type and point to the anomaly detection model as a part of your request body instead of part of the request. You construct the request body in JSON again by specifying the ID and make a call to /anomaly model deployments, which is the URL that you construct from the base URL. You make a post HTTP call again, containing all the details, and the output of this call will give you the response, which contains the deployed anomaly detection model. And how do you access it? That comes up, we come up to the end of the presentation, and I will be taking questions at this time. I have a question here. Which file formats do you support for training and detection? How about data sources? That's a great question. Thank you. We support JSON format, as you had seen during the demo. The JSON format contains the timestamps as a part of the body of the JSON, and also the values as floating point values within the JSON body. We also support CSV format for training, and we support CSV format for detection as well. As far as data sources are concerned, the service supports object storage as a first-party data source. We also support bringing in data using Oracle ATP, Automated Transaction Power Database. And we also allow connectors for various other data sources, including open source databases, such as time series databases, such as InfluxDB. You're always welcome to getting more feedback about what other data sources we have to support. Next question here. Where does the training data live, and how about the trained models? Training data always resides within the Oracle Cloud. Once the data is used for training, it can be removed from the cloud, and the model will function without any problems. The training data is only used for the duration of training, and once the training is complete, the model is an independent entity, does not have any dependency on the original data. Anytime you need to retrain the model, you need to upload the data again or create a new training request. The model, on the other hand, lies within the Oracle Cloud always, and it does not have any information about the original training data other than the metadata and statistical properties of the model. The next question. Can OCI AI services support real-time anomaly detection? That's a great question. The real-time anomaly detection can be supported using two scenarios. One is real-time anomaly detection using an application in between, wherein you use a dedicated cluster and continuously send data using an application in the middle. The second scenario is using OCI AI services and OCI streaming service, and in conjunction with OCI AI services. The combination of the two, you can create a stream wherein this data source is a real-time data source, and the output can be pointed to any OCI stream, including applications, dashboards, or notification systems. You can also plug in the output of OCI anomaly detection service through streaming servers to Oracle Analytics Cloud to enable visualization, slicing, and dicing of the data. Next question. What is the granularity of the data set required? Does the data need to be evenly sampled? It's a great question again. We support multiple granularities of the data. The data doesn't even need to be continuous as long as they are in the same order. For training, the IDP algorithms help in removing any intermittent faults or missing values in the training data that's coming in. And irrespective of the sampling rate, the final trained model is independent of the sampling rate of the training data or the detect data. There is no requirement of evenly sampling the data across training and detection, and multiple sensors can operate at their own frequencies. The service will still support it. Next question. Does the service only support time series data? That's a great question. And at this point, the service only supports multivariate time series data. In the future, we are planning to support non-time series data, including data in text logs and output of network monitoring systems, anywhere where there is no time element to it. We do not support it at this point, and as discussed before, the timeline is to be determined. And the question, how do you determine the model works correctly? Great question again. I will refer to the definition for false alarm and missed alarm probabilities. These two metrics are used to determine how the model works and how the model is, how the correctness of the model can be determined. A high false alarm probability means that the model is not working because there are information in the training data or within the model itself which is not giving you the right anomalies. Similarly, missed alarm probabilities are another metric, and high missed alarm probability value means that the model is skipping some otherwise real anomalies. Most of this can be done by, most of the fine-tuning here can be done by either fine-tuning the data or fine-tuning the parameters used to train the model. So I think we've come up to the end of this session. Thank you so much for attending the event and listening to the session.